In our previous lecture we introduced the concept of the gradient search based techniques, and we tried to illustrate one of those methods with the help of an example. So we will continue with that example. So in the example our objective was to solve the system of equation Ax equal to b, where A is given by this matrix and b is given by this vector. So what we first did is we first obtain Fx, which is half of x transpose Ax minus b transpose x plus c, and we plotted f in the x1 x2 plane. By setting c equal to 0 we satisfied that f will pass, the curve representing f will pass through 0 comma 0, and so it represented an ellipse with semi major axis length root 3 by 2 and semi minor axis length root 3 by 4. Now the method that we are going to describe on the basis of this example is known as steepest descent method. In this particular method, what we will try to do, we will try to move along the gradient of the function f, which represents the steepest rate of change or maximum rate of change of the function f, the direction of the maximum rate of change of the function f. We start with an initial guess. Let us say this initial guess is x1 0 equal to 0 and x2 0 equal to 0 as an example. Now in the next step what we will do, we will update this x. So we will come up with a new x. We will start from the x0 point, which is 0 comma 0, move in the direction of gradient of f and stop somewhere where the function is a minimum, and that will be the new iterate, that will be the new value of x. So x1, these are x0, so x0 means the vector x1 0 and x2 0. Now x1 is a point in this plane, x0 is another point, and the direction from x0 to x1 is along the gradient of f. Gradient of f and r have the same direction, but of course opposite sense, but it does not matter because the direction is the same. So we can say x1 is equal to x0 plus alpha 0 into r0. What is r0? r0 is gradient of f at x0, that is minus r0. So we have to find out, so what it says, x1 minus x0 is a vector which is oriented along r0 and which has the magnitude which is governed by the coefficient alpha 0. So you have to find out what is alpha 0. So what does alpha 0 tell? What does r0 tell? r0 tells what is the direction in which you are moving, that is gradient of f at x0. How much you are going to move along that direction, that will be given by alpha 0. So f of x1 is half x0 plus alpha 0 r0 transpose A minus B transpose x0 plus alpha 0 r0 plus c. For f to be minimum, you must have del f del alpha 0 equal to 0. So let us differentiate this with respect to alpha 0. So we have half of r0 transpose a x0 plus alpha 0 r0 plus half of x0 plus alpha 0 r0 transpose a r0 minus b transpose r0 equal to 0. So if you take alpha 0 common, here there are two terms which contain, each contains half of r0 transpose a r0 combined with alpha 0. So if you take alpha 0 common, it becomes r0 transpose a r0 plus half r0 transpose a x0 plus half x0 transpose a r0 minus b transpose r0 equal to 0. Now using a similar manipulation what we have done earlier also, you can show x0 transpose a r0 is equal to x0 transpose a r0, the transpose of that because it is scalar, that is equal to a r0 transpose into x0 transpose transpose is equal to r0 transpose a transpose x0, and that is equal to r0 transpose a x0, because a transpose is equal to a, we are dealing with a symmetric matrix. So a transpose and a are the same. So the second term and the third term combined together becomes r0 transpose a x0, and the final term b transpose r0 is equal to b transpose r0 transpose is equal to r0 transpose b. So if you combine all these, what you get is alpha 0 r0 transpose a r0 plus r0 transpose a x0 minus b is equal to 0. What is a x0 minus b? That is equal to minus r0, because ax minus b is r minus r. So this is minus r0. Therefore alpha 0 is r0 transpose r0 by r0 transpose a r0. So with this we can say that the new x x1 is equal to x0 plus alpha 0 r0. So you move up to certain x and that is the new x, x1, and then you change your direction. Similarly, when you go on calculating x2, the subsequent x, your alpha 1 will be r1 transpose r1 by r1 transpose a r1, and x2 is equal to x1 plus alpha 1 r1. In this way you go on having new choices of the point till you come to the solution. So till you hit the bullseye. So in the first step you move along the direction r0, in the second step you move along the direction r1. Interestingly, there is a very important relationship between these two subsequent directions, direction of r0 and direction of r1. To understand that, let us calculate r0 transpose r1. So r0 transpose r1 is b minus ax1. Because r is b minus ax, so r1 is b minus ax1. In place of x1 we can write x0 plus alpha 0 r0. So r0 transpose b minus ax0 minus alpha 0 a r0. What is b minus ax0? That is equal to r0. So this is equal to r0 transpose r0 minus alpha 0 r0 transpose a r0. Remember, alpha 0 is a scalar. So by using this relationship, alpha 0 equal to r0 transpose r0 by r0 transpose a r0, this becomes equal to 0. Okay. So r0 transpose r0 is equal to alpha 0 into r0 transpose a r0. So what does it show? r0 transpose r1 is 0. That means if you multiply the elements of r0 with the corresponding elements of r1, both are vectors, you get the result 0. That means just like physical vectors, it is like a extension of the dot product. It's a sort of an inner product, but if you consider it just from simple conceptual considerations, it is just like a dot product where you have the elements of r0 multiplied with the corresponding elements of r1 and the result is 0. So that means r0 and r1 are orthogonal to each other. So what we learned from this? First we moved along the direction of r0, next we will move along the direction of r1, which is x2 minus x1, and that direction will be perpendicular to this direction. In this way we will be moving in mutually perpendicular directions in several steps, maybe depending on how many steps necessary, till you reach the solution. So to understand how do we reach the solution using this steepest descent method, let us work out one or two steps maybe, and the remaining steps you can complete. So first step, what you have to calculate? You have to calculate alpha 0. That means you have to calculate r0 and r0 transpose r0 into and r0 transpose into a into r0. So your x0 is known, that is 0 0. So what is r0? B minus a x0. So that is equal to 1 1 minus that is 1 1. So R0 transpose R0 is equal to 1 1 into 1 1, so that is 2. Then R0 transpose A R0 A is 1 0 0 2 into R0. So 1, then so it becomes 3. So what is alpha 0? R0 transpose R0 by R0 transpose A R0. So that is 2 by 3. So what is x1? Is equal to x0 plus alpha 0 R0. So that is 0 0 plus 2 by 3 into R0 is 1 1. So 2 by 3, 2 by 3. Then you can calculate what will be the next calculation. What is R1? So R1 is B minus AX1. So 1 1 minus 1 0 0 2 into 2/3. Let us not go into again these lengthy calculations, because we have by this time understood that what are the sequential steps. Once you calculate R1, you can calculate alpha 1 and then you can calculate x2 by using these formula. So in this way you can calculate then alpha 2 and then x3 and so on till you find that you reach the solution. That means when you find that you reach the solution, your residual becomes 0. That is when you reach the solution. So as we can see through this example, that it requires a substantial number of steps. Even for such a simple equation, it requires a substantial number of steps to start with the initial guess point and to come to the final solution. This may be further improved, and the improvement of this aspect is considered in a method which is also a subclass of the gradient search based methods, that is known as conjugate gradient method. So let us look into the conjugate gradient method. And we will follow the method by using the same example that we have considered so far. So conjugate gradient method. So in this method, what is done? First you calculate up to x1, that is fine. then you try to make a modification. What modification? See, what we do, we first calculate x1 and then we see that it requires a lengthy number of steps to reach the final solution. So then somebody who is very greedy wants to get a solution in one step, that is wants to get to the solution from the point x1 directly. So let us say this point is called as xc, the center of this ellipse, which is the solution. Reaching this point means reaching the solution. So in one step, if you want to move from x1 to xc, so what you do is you do not go through all these steps, in one step you want to reach this solution. Then what is the direction in which you move? You move in a direction which is directed from x1 to xc. So you move along a direction given by say p1, which is a new variable, which is k into xc minus x1, where k is just a scalar, because how much you have to move is something which is to be determined, but at least the direction is known from x1 to xc. So position vector of the second point minus position vector of the first point. Because you introduce a new variable p1 and you intend to move along that direction, you also have something which is p0 and which you call same as r0. So p0 is same as r0, because for the initial direction you do not have any difference in terms of the direction in which you move for the steepest descent method, but from the subsequent steps you try to change your direction. So you have p0 equal to r0, p1 equal to k into xc minus x1. Now you can write a p1 is equal to k axc minus ax1. Why you write it in this way is because you can then write it in terms of the residual. What is axc? Axc is equal to b, because xc is the correct solution. So axc minus ax1 is b minus ax1, which is equal to r1. So this is k r1. You know that r0 transpose r1 is equal to 0, which we have just proved. So if you multiply both sides by r0 transpose, then it will become 0. So r0 transpose ap1 is equal to k r0 transpose r1, which is equal to 0, and r0 is nothing but equal to p0. So we can write p0 transpose ap1, that is equal to 0. So p0 transpose p1 is not 0, but p0 transpose ap1 is 0. So this is in linear algebra terminology is called as p0 is a orthogonal to p1. Just a name. Now despite having a relationship between p0 and p1, this alone does not give you any clue of what is p1, because that is essentially your interest, that what is the next direction in which you are interested to move. Once you reach x1, from x1 in what direction you are interested to move. So you have to know what is p1, and at the most what you have in your hand, you have r1 as one direction and p0 as another direction, which is same as r0. So you form p1 as a linear combination of r0 and r1 and try to satisfy this relationship. So you form p1 as r1 minus beta 1 p0. So the whole purpose is that you are going to have a new direction. This new direction you can form by taking help of some known directions. Known directions till now are R0 and R1. R0 is same as P0. So you make it as a linear combination of these two, and this is known as Graham-Smith conjecture. So then P0 transpose A into R1 minus beta 1 P0 is equal to 0. So you have beta 1 as P0 transpose A R1 by P0 transpose A P0. So if you know beta 1, then using beta 1 you can find out what is P1. But the next thing is that you know that therefore the direction in which you want to move, that is P1, but how much, that the next you have to find out. So next you have to find out that what is the next point x2. X2 is equal to x1 plus alpha 1 into P1. See, here lies the difference between the steepest descent and the conjugate gradient method. In the steepest descent method it was alpha 1 R1, so you moved along the direction of R1. Now you are not moving along the direction R1 but a different direction P1 with a hope of reaching the point, the target, the solution directly in one step. Okay. So the question will remain that what is this alpha 1? Again the basic principle is the same. Alpha 1 should be such that f should be a minimum. So f at x2 is equal to half of x1 plus alpha 1 P1 transpose A x1 plus alpha 1 P1 minus B transpose x1 plus alpha 1 P1 plus C. Just substitute in place of x as x2, which is x1 plus alpha 1 P1. So for f to be minimum, del f del x2 should be equal to, sorry, del f del alpha 1 should be equal to 0. So what we get from here? Half of P1 transpose A x1 plus alpha 1 P1 plus half of x1 plus alpha 1 P1 transpose A P1 minus B transpose P1 equal to 0. So we can now simplify. You can see that first you have with alpha 1 P1 transpose A P1 half of that, and then again another P1 transpose A P1 half of that. So alpha 1 into P1 transpose A P1 plus half P1 transpose A X1 plus half X1 transpose A P1 minus B transpose P1 equal to 0. So, alpha 1 P1 transpose A P1 plus now you can reorganize this term as we did earlier, you can take a transpose of this. So, if you take a transpose of this, it will become P1 transpose A transpose X1 and A transpose is same as A. So, plus this will become therefore half P1 transpose AX1, this is another half P1 transpose AX1. So, total is P1 transpose AX1 from this term and the last term B transpose P1 is same as B transpose P1 transpose. So, P1 transpose B. Okay. So, P1 transpose AX1 minus B, that is equal to 0. AX1 minus B is minus R1. So, the formula for alpha 1 that we get here is P1 transpose R1 by P1 transpose AP1. How to implement this in practice? Let us follow the previous example using which we will try to illustrate. So, the same example where we have A is equal to 1 0 0 2 and B is equal to 1 1, we have to find out what is the value of x. So, remember that the first few steps of the conjugate gradient method are same as the first few steps of the steepest descent method. Up to which steps? First calculation of R0 which is already there, then alpha 0 and x1 is equal to x0 into alpha 0 R0 and R1 B minus AX1. So, we will require R1 and R0, therefore, let us complete the calculation for R1 before we proceed further. So, R1 is B minus AX1. So, 1 1 minus 2/3 and 4/3. So, what will be R1? 1/3 and minus 1/3. So, up to these steps we also had to calculate in the steepest descent method. Now, in the conjugate gradient method the subsequent steps will require what? Next you will require the calculation of P1, for that you need to calculate beta 1. So, let us calculate what is beta 1. Remember that R0 and P0 are the same. So, R0 this is equal to P0. So, next let us calculate what is beta 1. To do that, what we need to calculate? Numerator P0 transpose A R1, P0 transpose A R1, this is equal to 1 1, this is P0 A R1 1/3 minus 1/3. This is 1/3 minus 2/3. So this becomes 1/3 minus 2/3 minus 1/3. Then denominator in the formula for beta 1 is P0 transpose A P0. So P0 transpose A P0. We have already calculated it in the steepest descent method, because P0 transpose P0 A P0 is same as R0 transpose A R0, because P0 and R0 are the same. So let us not just waste any time for calculating it, we have already calculated it. So this is same as R0 transpose A R0. So for that we have the result already as 3. So beta 1 is equal to P0 transpose A R1 by P0 transpose A P0 is equal to minus 1 by 9. So that will lead to the calculation of P1. P1 is equal to R1 minus beta 1 P0. So R1 is 1/3 minus 1/3 minus beta 1, so plus 1 by 9. P0 is same as R0, that is 1 1. So this becomes 1/3 plus 1 by 9, so 3 plus 1 4 by 9, and minus 1/3 plus 1 by 9, so minus 3 plus 1 minus 2 by 9. So once you have calculated P1, what you next should calculate? Alpha 1. So for calculation of alpha 1 you require in the numerator, so this is the formula for alpha 1. This is the formula for alpha 1. In this particular formula you require P1 transpose R1 and P1 transpose AP1. So P1 transpose R1 is equal to P1 transpose R1, R1 is 1/3 minus 1/3. So 4 by 9 into 1 by 3, that is 4 by 27 minus, then sorry, plus 2 by 9 into 1 by 3 plus 2 by 27. So that is 6 by 27, that is 2 by 9. P1 transpose AP1. So 4 by 9 minus 2 by 9, A 1002 and P1 4 by 9 minus 2 by 9. So this will become 4 by 9 and minus 4 by 9. So 4 into 4, 16 by 81 plus 4 into 2, 8 by 81, 24 by 81, 8 by 27. So next we can calculate what is alpha 1. Alpha 1 is P1 transpose R1 by P1 transpose AP1. So 2 by 9 by 8 by 27. So 2 by 9 into 27 by 8, that is equal to 3 by 4. So x2 is x1 plus alpha 1 P1. What was x1? x1 was 2/3 and 2/3 plus alpha 1, that is 3/4 into P1, 4 by 9 minus 2 by 9. So that is 2/3 plus 3 by 4 into 4 by 9. That is the first point. So 2/3 plus 1/3, that is 1, and the other point is 2/3 plus 3 by 4 into minus 2 by 9. There is some 2 by 3 minus 1 by 6. So that is equal to half, right? So you can see that in one step it has reached the solution. Okay. So the conjugate gradient method is supposed to work with a greater speed for reaching the solution. Speed means less number of steps, that is what we call as speed, it is not the computational speed. Now we have seen the gradient search based methods, that is the steepest descent method and the conjugate gradient method. Now let us try to assess the applicabilities of these methods. So let us work out one or two examples to see how they work, how efficiently they work, and so on. So let us consider a problem. Given a matrix A, the eigenvalues of which are negative, an analyzer tries to apply the gradient search based methods for solving the system Ax equal to b. How do you assess the success of that attempt? The chance of success in that attempt. So, in many cases people try to use a method, in many cases people are unsuccessful because they have implemented the method wrongly. In some other cases they are unsuccessful because the method is wrong for that particular situation. So, when you say the question how do you assess the chance of success in that attempt, you have to assume that otherwise if he or she implements the method there is nothing wrong with the implementation. Of course otherwise you can say that I assess that there is no chance of success in the attempt because the person is very dull or inefficient. So, it's not like that. So, you have to assume that the person is very efficient in terms of implementing the method as it is. But even then whether you expect success or not, that is what you have to predict. So, the clue should come from this particular statement, the eigenvalues of which are negative. So, what is the consequence of a coefficient matrix which is having negative eigenvalues? So, you have Ax equal to b and the corresponding eigenvalue, if you have lambda for the matrix A, then you have Ax equal to lambda x. Now, for the gradient search based methods you have to recall that what are the basic conditions that need to be satisfied for the method to be applicable. One is A has to be symmetric, another A has to be positive definite, because we have shown that the symmetric condition is good enough to have the gradient of the function f equal to 0 corresponding to Ax equal to b, but that does not ensure a minimization. A minimization on the top of that is ensured by a positive definiteness of A over and above the symmetry requirement. So, we have to ensure that A is positive definite. How do we ensure? If you have an arbitrary vector x, then x transpose Ax should be greater than 0. Now, if you have x transpose Ax here, that is nothing but lambda into x transpose x. What is x transpose x? It is positive or negative? It is always positive because an element of x is multiplied by the corresponding element of x only. So, x transpose x is what? You have x1, x2 in this way xn, that is multiplied with x1, x2 in this way xn. So, it is lambda into x1 square plus x2 square. So, it is just like making a dot product. Now, this will be negative here because this is positive but lambda is negative. So, this is negative. Even if one eigenvalue is negative, that can make this corresponding x transpose Ax as negative. So, that means it is not A is not positive definite, which implies that the gradient search based methods will not work. Fortunately, in computational mechanics problems, most of the coefficient matrices that you derive from the discretization of a physical problem, many of those will be symmetric and positive definite, and therefore you can use this method. But you have to keep in mind that that is not an assurance. You have to first assess whether the coefficient matrix is symmetric and positive definite. Symmetry assurance is obvious, you can just directly observe and find out whether it is symmetric or not, but for assessing the positive definiteness you have to be a bit more careful. Let us consider another problem. Compare the steepest descent and the conjugate gradient method with regard to the solution of this. So let us find out what is Fx, half of x transpose Ax minus b transpose x plus c. So half of x1 x2 into 1 0 0 1 x1 x2 minus b transpose x plus c. This minus x1 plus x2 plus c. So half of x1 square plus x2 square minus x1 plus x2 plus c. To have a visualization of the method, we will try to plot f equal to 0 in the x1 x2 plane, as we have done in one of the previous examples. So to do that, we will write half of x1 square minus 2 into x1 plus 1 plus half of x2 square minus 2 into x2 plus 1 plus c. So f is equal to half into, okay, there is one adjustment of minus 2, right, plus c minus 2. So half of x1, so half plus half 1, sorry, yes, so minus 1. So half of x1 minus 1 whole square plus half of x2 minus 1 whole square plus c minus 1. So if you want to have, if f equal to 0 passes through 0 comma 0, which is your initial starting point, then you have 1 square plus 1 square, sorry, half into 1 square plus 1 square plus c minus 1 is equal to 0. That means c equal to 0. So then you have half of x1 minus 1 whole square plus half of x2 minus 1 whole square is equal to 1. So x1 minus 1 whole square plus x2 minus 1 whole square is equal to 2. Right? So it represents what? Represents a circle in the x1 x2 plane. Circle has center of 1 1. So this is 1 comma 1 and radius of root 2. It is very difficult to draw a circle. Every time you try to draw a circle it becomes an ellipse. Maybe if you try to draw an ellipse it becomes a circle. But let us try to understand the basic essence out of it. So you have the starting point 0 comma 0. This is the bullseye that you have to hit, you know this is the solution. So in the steepest descent method you are moving along the direction of the gradient of f, which is what? Which is normal to the curve. So you move along this direction, so you will definitely hit the center, because in one step you are able to reach your goal. The steepest descent and the conjugate gradient method for this case will be the identical. So when you say compare the steepest descent and the conjugate gradient methods with regard to the solution of this, they are absolutely identical, because in this special case you are lucky enough to have it as a circle where the normal direction and the radial direction are the same, so that you reach the center in one shot. So this is a very special example, a very simple example where you can say that in identical steps you can reach the solution for both the methods without working out the further details. So we stop our discussion on the solution of the system of algebraic equations here. So far we have studied the diffusion type of problems, their discretization and solution of the discretized algebraic equations. So our next agenda will be to go one step forward and try to see how we discretize the convection diffusion problems. That we will do in the next class. Thank you.